Welcome, ladies and gentlemen, to our lecture on kinematics in multiple dimensions. Remember that last lecture we talked about using these kinematic equations to describe motion with constant acceleration in one dimension. Today we're going to talk about generalizing these equations to solve for systems with constant acceleration, but with motion in multiple dimensions. So let's consider a coordinate system like this. Our standard Cartesian x and y coordinates, where the x and the y-axis are orthogonal to each other or perpendicular to each other. So no part of the x points in the y direction, no part of the y points in the x direction. And then let's remember our main kinematic equation. Remember, I told you this one was the most important of the kinematic equations that I showed you. And we derived all the other ones from this one. So this is how we wrote this equation repeatedly. But the truth is that all along it was actually this. So what do we have here? We have positions that are vectors. So they actually look like this. They have position in the x, position in the y, and position in the z. Okay? We have velocities that are vectors. So they have a piece that's in the x direction, a piece that's in the y direction, and a piece that's in the z direction. Okay? And we have accelerations that are vectors. So they have a piece that's in the x direction, a piece that's in the y direction, and a piece that's in the z direction. So remember that these things are always vectors. They always look like this. When we write this equation, we often don't write it with the vector symbols, but we should always remember that these are vectors. So notice that in this equation, I have these vectors, but I don't have any vector products. These vectors are all just multiplied by a scalar, by time, or by some number in this case. Okay? So there's no dot products in here, and there's no cross products. That means that when we have a coordinate system that's orthogonal, we finally get to the reason that I kept saying we always want to make sure that our coordinate systems have orthogonal directions. Okay? When we have a vector equation like this, with no vector products in it, no dot products or cross products, this equation actually represents a system of equations in an orthogonal coordinate system. Okay? So this equation doesn't just mean this one equation. In this case, in the Cartesian coordinates in 3 dimensions, it means 3 equations. So with our independent axes, we end up with an equation, remember like we had before, in the x direction, okay, like we had with one dimension, but now I'm noting here that these two are the x components of the initial velocity and the acceleration. But we also have the same equation in the y direction, independent of the x direction. And if we had a z-axis, that would be true for the z as well. So what we end up with is multiple independent equations, or a system of independent equations, out of this one vector equation. So we kind of get 3 for the price of 1 here. So with our axes that are independent of each other, it's important to remember that all the things that we discussed before that were true in one dimension, they're still true. So these 4 equations are now true in each coordinate in the Cartesian system. So each of these equations is true in the x direction, in the y direction, and in the z direction. It's also true that our description of velocity as the rate of change of position and of acceleration as the rate of change of velocity still hold. So remember, if we wanted to know velocity, we would take the derivative with respect to time of position. That was true in one dimension, and it's still true here. So what this piece means is that we take the derivative of the x component with respect to time. We have the derivative of the y component with respect to time. And we have the derivative of the z component with respect to time. And that will give us this vector velocity with components in the x, y, and z directions. And then if we want acceleration, we do the same thing to that velocity vector to get the acceleration. It's also true that our conditions for applying these equations are still the same. So we still require a constant acceleration, or in other words, dt of a equals 0. It's not a function of time, it's constant. So this generally means that something is driven at a constant acceleration. Okay, and by driven I mean it's pushed along at a constant acceleration by some input of force, okay? Or it's driven by gravity and we have air drag that's limited enough that we can neglect its influence. So from this point forward, it's always very important to pay attention to both the magnitude and direction of all of these vectors. In particular, as we break it down into individual components, say motion in the x direction and motion in the y direction, it's really important to remember which direction you said was positive so that you can add negative signs to motion that goes in the other direction. So if I say that x is positive when it moves to the right, when I have something that's moving to the left, I have to remember that that is actually negative x. So our most common example of kinematics in multiple dimensions is projectile motion. When we say projectile motion, what we mean is objects flying through the air with only gravity acting on them. Okay? So what we mean is that first, air drag is going to be negligible. So it either doesn't exist if they're in a vacuum, or the effect is small enough that when we ignore air drag, we only make our calculation off by a little bit. So this requires that things aren't flying too far. If they're flying too far and they accumulate too much acceleration downward, if they accumulate too much speed from their acceleration downward, they'll start to have big air drag, and that'll start to affect our calculation. If they're flying too far, we would start to care about the rotation of the Earth, but they have to fly pretty far for that to be true. And we have to have them flying at kind of relatively low speeds to use this without acceleration. The reason that we consider projectile motion without air drag in this class is that it actually becomes very complicated with air drag. The mathematics is much more difficult with air drag than it is without, and we're not prepared to deal with air drag in this class right now. So we will use the approximation that there's no air drag. So we'll deal with things moving at lower speeds, and we'll deal with the fact that we know that our calculations might be off by a little bit as things speed up and we are still ignoring air drag. Okay? So we can think of things like tossing a ball or a person jumping through the air, or similar scenarios where we have a relatively dense object moving at relatively low speeds. So let's look at projectile motion. Let's think about throwing a ball, and it has we give it some initial velocity, and then it flies through the air over here. Okay? And it's really common in projectile motion to describe this initial velocity vector with a speed v0 and an angle above the horizontal. Okay? This is our most common way to describe the initial conditions for projectile motion. So notice that if I set up a coordinate system, x hat and y hat, where y is totally perpendicular and x goes along the ground, it's totally horizontal, then when we have gravity that always points straight down, notice the gravity is only in the y direction. So we said before that with our orthogonal coordinate system, the motion in the y is completely independent of the motion in the x. And that means the effect of gravity is completely independent of motion in the horizontal direction. Okay? This turns out to be true in the physical world. I think that your book has a really nice video where the guy doing the demonstrations has two balls, and he throws one ball straight out horizontal like this, and he drops the other ball at the same time. So the balls kind of fly like this and like this down to the ground. And it actually is true that these two balls hit the ground at the same time, because this initial velocity in the horizontal direction, it doesn't affect the vertical motion at all, which is where the acceleration from gravity comes from. And all that actually matters for how long it takes me to hit the ground is my acceleration in this vertical direction, right? My initial velocity and my acceleration in this vertical direction, that's what decides how long I'm going to be in the air. So it does turn out that it is the case that these two balls hit the ground at the same time. And this is our first really nice example and really impactful example where we looked at the mathematics and we saw that with our orthogonal directions, the x component and the y component should be totally independent. And then when we go out and test it in the real world, that is indeed true. The vertical motion and the horizontal motion, they're completely independent. And it isn't just true in this example where he has these kind of balls that are flying very slowly and things like that. This one is always true. This one would be true even if we had a bullet fired out of a gun in a totally horizontal direction and a bullet that we just dropped. It would still be true. We would still have the two bullets hit the ground at the same time. This is a really significant result and a really interesting one to see. So now let's go back to our projectile motion example. We have vertical motion and horizontal motion that are completely independent of each other. I picked this coordinate system where x goes horizontal and y is up, y is vertical. And we know that in kinematics, we have this equation. And remember, I told you that we usually write it like this, but in truth, it means this. Okay? So the last thing our coordinate system needs is an origin. So let's pick an origin such that x0 equals y0 equals 0. Just to simplify things. And then let's look at this system a little bit, okay? So our origin is right where the ball starts. So at any point along the way, at any point in the x direction along the way, here, 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 it's going to be true that x equals x0, which is 0, times v0 in the x direction, or what, plus v0 in the x direction times t, okay? Plus 1/2 and then a in the x direction, but that is also 0 because our only acceleration in this problem is g, which is totally in the vertical direction. Okay? So this is going to describe our x position at any time t. And then let's do the same thing for the y. So our y position at any time is going to be y0, which is 0 in this coordinate system that we set up, plus v naught in the y direction times t. And then notice that g is down, and I said that y hat was up, okay? So ay equals minus g, okay? So we have minus 1/2 g t squared. And that is our motion in the y direction, okay? I can manipulate this x direction equation algebraically and say that t equals x over v naught x, okay? And then I can stick that into our y equation. So y equals v naught y, and then we replace t with something that's equivalent, okay? And now what I have is I have the y position in terms of the x position. So at any point, if I know the x position, I can calculate the y position. And I can express that. I can just rearrange a little bit and express it like this. Okay? And then let's replace that one more time. Let's call this piece, that's just some number, right? It's just some number a times x. And then minus, and then this piece, again, that's just some number, right? We'll call it b times x squared. And this equation right here is the equation of a parabola. A parabola has this shape, as best as I can draw it anyway. It's symmetrical, and it describes projectile motion. So projectile motion is shaped like a parabola. And this example was totally general, right? So this is always true. Our projectile motion, when we ignore air drag, is always going to be shaped like this parabola. That's the way things are going to fly through the air when they're affected only by gravity, okay? So now let's consider an example to look at kinematics in multiple dimensions, okay? Here's our example. Remember Cool James from our example in one dimension? He was the pitcher who could throw a baseball 55 miles per hour. When Cool James is throwing for distance, he releases the ball at a point 6 feet above the ground. If the left field fence is 200 feet from home plate and is 6 feet tall, can Cool James throw the ball over the fence from home plate? So this gives us a nice example to look at this. And the first thing I want to do with this question is figure out something that's very general, okay? So first, let's draw it. We have a ball. We have some height 6 feet where he releases it from. And then 200 feet away, we have the wall, okay? He's going to throw it like this. And it's going to go like this if he can throw it over the wall. So this one is 60.96 meters. It's 1.83 meters, okay? And he throws it at some angle theta above the horizontal. So notice they didn't tell us what angle above the horizontal he throws it. They just asked us, could he possibly throw it over the wall? So let's pick a coordinate system. And I'm going to pick the one again where x hat goes along the direction of the ground. It goes horizontal, and y hat is vertical. I'm going to pick the origin at the starting point of the ball so that x naught equals y naught equals, in this case, y final because the wall is the same height. So in the end, we're ending this consideration at the same height that we started, and that's 0. Okay? So we picked our origin such that x naught, y naught, and y final are 0. We know that v naught is some particular speed. Okay? And we know that x final is some particular distance. And we know that a equals minus g equals minus 9.8 meters per second squared. Okay? And then they want to know if he can throw the ball over the fence from home plate. So they want to know, is x max greater than x final? Okay? So there we go. So now we're going to solve this with 2D kinematics. Which means we're going to use this equation right here. And again, remember that in reality, I'm always going to probably write it like this, but we know that it actually means this. So now, let's consider our motion in the x direction. Okay? So let's consider that he throws it as far as he possibly can. They haven't told us what that angle is, but we can imagine if we vary this angle, theta, up and down, it must go further for some angles and shorter for other angles, right? If we keep this velocity the same. We don't know what that max is, but it must be some value. So the first thing I want to consider is, in this example where the initial height and the final height are the same, what is that angle? What angle produces the maximum distance? So let's say, just for now, let's use the notation xm equals x max, okay? So if I plug the x motion into our kinematic equation up here, I get xm equals, remember x naught was 0, so v naught x times t, and there's no acceleration in the x direction, so ax equals 0. So this is our motion in the x direction. Now remember, at max, when it lands, it's back to height 0. We said y final equals 0. Y naught equals 0. We have v naught y times t. And then remember, our acceleration is minus g. So we have minus 1/2 g t squared. Then we can manipulate this to say that v naught y t equals 1/2 g t squared, and that tells us that t equals 2 v naught y over g. So our vertical motion has dictated the time that we're in the air, and we stick that into our equation for x max here. To figure out what x max is. So as an aside for a second, think about, we're throwing the ball with some initial velocity here, v naught. We have the horizontal direction here. We have some angle, theta, above the horizontal direction. That means that we have an x component, vx, that goes horizontal, and a y component, vy, that goes vertical. If we use our trigonometry that we practiced in the math prep homework, we'll know that vx equals v naught cosine theta, because Vx is next to this angle, right? And V naught y and V naught x equals V naught sine theta, okay? Just by using our trigonometry. So let's use that and plug it back in to this equation over here. So then this equation is equal to 2 V naught squared, remember both had V naught in front of them, over G times cosine theta times sine theta. Okay? Now, there's a trick that you might remember from calculus where if I want to find a local maxima or a local minima, a local extrema they call it, I can take the derivative of something and then set that derivative equal to 0. So if I take the derivative of xm with respect to theta, what I'm finding is the rate of change that we have for xm when theta changes, okay? And when I set that to 0, I'm going to find a maximum for this. So this first piece, remember, when we take the derivative, none of that depends on theta, so that's just a number as far as this goes. So we'll just carry it down. Okay? And then when I take the derivative with respect to theta with this piece, what I end up with is cosine squared of theta. This squared, if you haven't seen it before, when we square cosine and sine, we put the 2 before the angle just to make it clear that we're not squaring the angle, we're squaring the function cosine. Okay? Minus sine squared theta. And again, we're going to set this derivative equal to 0. Okay? We're going to impose that condition on it. So we're forcing that to be true, because that's how we find a local maximum. But if that's true, if this equals 0, then this piece here isn't important, right? What this is telling me is this inside here must be equal to 0, because we know that this piece isn't, right? It has some initial velocity that's greater than 0. We know little g is not 0. So that piece can't be 0, which means that this other piece over here, the cosine squared and the sine squared, that sum must equal 0. So for that to be true, that means cos squared theta equals sine squared theta. Okay? If I take a square root of each side, I have cos theta equals sine theta. Okay? And we know that when we throw this ball, it's going to have an angle between 0 and 90 degrees. Okay? See up here we have 0 totally horizontal and 90 straight up in the air. I know it's not going to have an angle bigger than 90 because then it would be thrown the other way, and then I would just redraw my picture so that I consider motion in this direction, right? And I know it's not going to have an angle that's negative because we're throwing it up through the air. So I know it's not going to be like this. We're not spiking it into the ground. So I know my angle must be between 0 and 90 degrees. And I know that I've shown that this must be true. So there's just one angle for which this is true, and that angle, theta, for max distance, when the starting height and the finishing height are the same, is 45 degrees. Okay? So that's a general result that we've determined here. And our general result is, if our starting height and our finishing height are the same, and we know some fixed initial velocity, then the maximum distance for projectile motion is when we launch it at a 45-degree angle. So now we have our general result. When we launch and land at the same height, theta max is 45 degrees. And remember, it asked us, can Cool James throw it over the fence? So the furthest he could possibly throw it is if he throws it at a 45-degree angle. And if we look here, we've actually already solved for the max distance that he can throw it. So all we really want to know is whether this xm is greater than 60.96 meters. So first, let's check units on our answer. We have meters per second, and that was squared on top. And then on the bottom, we had meters per second squared. Okay? And cosine and sine don't have any real units. So this equals meters, which is what xm should be. So that works. Sanity, xm increases as v naught increases. So if he could throw it harder, our equation says that he would throw it further. And that makes sense, right? If he can give the ball a bigger velocity at the beginning, he'll throw it further. Okay? xm goes down as g goes up. Okay? So that tells us if the acceleration due to gravity were stronger, he wouldn't be able to throw it as far. And that makes sense because we'd have a bigger acceleration in the downward direction and it would pull the ball back to the ground faster, right? At each moment in time, it would give it a bigger increase in velocity. And in the end, what would happen is we wouldn't fly for as long, so it wouldn't go as far. So that makes sense too. And so when we plug in numbers, what do we get for xm? We get 61.7 meters. And that is greater than our 60.96 meters, just barely. So it sounds like Cool James could actually just barely throw it over the wall out there in left field where it's 200 feet. So over the next couple days, I'm going to go over some additional examples of problems with kinematics in multiple dimensions to really help you familiarize yourself with solving problems of this type. And even more importantly, your homework is going to have a number of these problems for you to practice on so you can really learn these concepts.